Hi guys, some of you have said, this is Jane working from home, some of you said you had trouble with some of the internal resistance questions. Here are the internal resistance questions, so I'm just going to try and explain some of them to you. So, and also a little bit about internal resistance, because I think some of you are struggling with that a little bit. So basically, generally in a lot of questions we say assuming no internal resistance. And what we mean by that is that the cell or the energy supplier, whatever that is, has no energy lost in the circuit. So all that's available, say 1.5 volts here, is dissipated throughout the circuit. But when in reality what happens is in the battery or in the cell, some of that energy per coulomb, if you want to be specific and correct, is used up, so generally through heating or something like that. So you get a little bit of that energy per coulomb used up in the cell. And to explain how that's used up, we say there's a little internal resistor, and we often draw a little internal resistor like that, and we sort of add it in like that and say there's a little internal resistance in the circuit or in the cell. And so even though there was originally 1.5 volts available, some of that energy per coulomb is going to be used up here. And I often call that little v. And then I'll call the one across the whole thing, I can't quite draw it on there, big V, like that. Now the energy actually available is the EMF. And I've kind of said that. So that's the energy available at the start. So it's the energy available by the power supply if no current goes through it. So if you think about energy conservation, the energy available at the start, can you see that, is going to be used up in the circuit. So there's going to be a little bit used up across the resistor in the internal resistance and a big bit used up across the whole circuit. So that's just conservation of energy. So you can write that as EMF is equal to I little r, because we know that V is IR, and that little voltage is like saying that little one there. So that's like the little voltage across that little resistor there, the internal resistor, if there was such a thing. And you can call that IR, and you can call that one I big R. So you can either use that equation or that equation, depending on what's the easiest. And just a quick recap on yesterday's lesson, we rearranged that in the form of, we used this one, and we used EMF is equal to IR plus V, and then we varied I and we varied V, and then we rearranged that so that we had V is equal to minus R I plus EMF, and then we used Y equals MX plus C, like that. And so on the y-axis we've got the V, on the x-axis we've got the I, and then we've got a negative gradient because it's negative, so it's going to be going downhill, and big gradient, and the gradient will be minus R, and where it crosses there is the EMF. So what you do is you have a variable power supply, and you measure V and you measure I, and then you plot the graph, and that's what you get. And that's what I asked you to do in your first assignment. So hopefully you've got that. So that's how you get the EMF and the internal resistance from a graph like that. Now I'll go on to answer the questions.